H2 potential energy. And we're going to consider gravity first. So this applies when you have conservative forces. For a conservative force, since you can get back the same kinetic energy, what we say is, and we'll give gravity as the first example, then we'll do the spring, that if you were to take this mass and bring it up to, say, a height h, or let's say that you tossed it up in the air. So if you tossed it up in the air, it would then, when it comes to rest momentarily up there, we say it has potential energy to come back down and get you your kinetic energy back. Or if you just pick it up and leave it and hold it there for a second, we say it has potential energy to get kinetic energy if you let go. So that's the whole idea there. So the work, let's say the work here, and let's go ahead and say we're just going to pick it up from the ground. We just pick it up from the ground using mg to gently get it up there. Then you have the work done as mgh. Then the work energy theorem here, if you let go the conservative force, you're going to have gravity working on you with an mg. So if you consider going down as positive for the second part of the problem, then gravity will be given a force mg down, and you'll move through a height h. So that's the work you'll do coming down, and that's going to equal to 1/2 mv squared, because remember the work energy theorem says that the work that you do is equal to the change in the kinetic energy. And since we're starting here from rest, this initial kinetic energy is going to be 0 because that velocity is 0. So if we look at this, we could say that before you have potential energy, the energy before is equal to mgh, and the energy after, that's after it falls, is about to hit the ground, is 1/2 mv squared. And then you can write the work energy theorem as the energy before, or you could say energy at point 1 is equal to the energy after, or the energy at point 2. So you can think of this energy as now a combination of the kinetic energy plus the potential energy. Before, when the ball is up there, you have a height, but you have no velocity. So that's the mgh, using the master formula. So you put in the 0 for the v. Then afterwards, when you get right before you hit the ground, the h is 0, the height is 0, and then you have the 1/2 mv squared. So we can say that the total energy is equal to the kinetic energy plus the potential, which we use the letter U to designate potential energy, where the U for gravity near the surface of the Earth is mgh. Some books like to say mgz, where z is a variable, and you're measuring z from the ground. So at the ground, z is equal to 0, and then you measure going up. It'd be nice to be able to relate this conservative force that's due to gravity, and in this case, if we're choosing up to be positive, to write this nice equation like this, measured from the bottom, the ground, then the force is minus mg due to gravity. And we like to be able to relate these two together, and we could see that the force is given by negative the derivative of the potential energy function with respect to z. That's the variable that measures the distance from the ground. So that's the connection you take the derivative of the u and you get mg, and then you put a minus sign in front, then you get your force. Now when you have friction, just remember that you don't have a potential energy, this would not work, but energy is conserved in the sense that the loss of kinetic energy would, like if you started something and had friction, that it would go into heating up the blocks, say, for example, or the table that we did before. So energy is always conserved, but when we say conservation of energy in the context of these problems, we mean that the potential energy plus the kinetic is a constant. So now we're ready to do the second case, the spring. And for the spring, let's look at here the spring that's pulled aside. Say here is the reference where x is equal to 0. So then the x is the stretch or the compression. To compress, the x is going to be negative. So since I have this pulled to the right, that would be a positive x in this case. So then Hooke's law says F is minus kx. Now we'll do the same thing we did here, same idea. We picked up this and then we let it go. So we did the work mgh, and the conservative force brings, that mgh come back when it comes down. So if I do the same thing here, and we looked at this in an earlier section where we looked at the force, and we had here the force. This is the force that I need to apply. Okay, so this is the force I'm going to apply to counteract this force. So the force that I apply, that's going to be a plus kx, and that's going to go up like this, say. And here, this is your x axis, and say, we pull up x. This is the force, and this height here is kx if we go to the point x. So we want the area under the graph like we did earlier. So that would mean that the work that's done is 1/2 the base times the altitude, and that's 1/2 kx squared, which we know from an earlier section. And then we show that we showed earlier that when we release it and the spring does the work, you get the same thing back. And that's the idea of a conservative force, that you get the same energy back. So this is the potential energy when you stretch, and then when you let it go and come back, you're going to have some velocity at the 0 point, and then it will overshoot and it will go in and it will oscillate, which we'll study later. So in this case, the potential energy is going to be equal to 1/2 kx squared, and that's for the spring. And we ask ourselves the question, does the derivative rule with the negative sign get you the force, which is what happened up there? So if we take the force and we're going to ask the question, does this come from negative, the derivative, with respect to the variable, which in this case is x? So that's negative the derivative. Potential energy is 1/2 kx squared. So if you differentiate x squared, you get 2x. So 1/2 k would just float right out. So this should be 1/2 k, the derivative of x squared, and that's going to give you 2x. Then the 2's cancel, and you get minus kx, which is the force. Like, yes, it checks out. So that's a very, very nice, let's say, confirmation that we have a good physics that we're doing here.